Performance in this high-level organic chemistry test is usually a bit of a mixed bag. People who either do really well because they've learned all the mechanisms, learned all the details, and do quite well. People who are not quite there yet tend to struggle. And I go through it now. Hopefully, you make your corrections and learn from them. So, alkenes, what's not correct here? So, alkenes. The whole point about alkenes is they have double bonds, and those double bonds have got a sigma bond and a pi bond, and that pi bond, the electron density is a bit further from the nuclei than the sigma bond, which makes them quite reactive. So it ain't that one, because double bonds are quite reactive. They can form addition polymers, GCSE stuff, so I'm not going to draw that out right now. They react by substitution. Well, they don't. They react by addition reaction. So for example, you can add HCl to, say, ethene, and you'll get an addition reaction with the hydrogen adding to one carbon and the chlorine. So the answer is C there. If you've got a tertiary halogenoalkane, it will undergo SN1 mechanism because you form that transition state and the carbocation intermediate, and that's what that is there. So the intermediate is the carbocation. So the bromine missing and the carbocation left behind, so you've got a carbocation intermediate. So that one. Which one has a chiral centre? Well, to do this question, really you have to be able to draw out the molecules to give yourself any kind of a chance here at all. So you can either draw them kind of semi-displayed like this, I suppose, for the sake of an exam. But one thing that I think people forget is that CHO, that's an aldehyde, so it's like that. And so a chiral centre has got a carbon with 4 different things coming off it. There's no carbon like that there. This molecule here, again, draw it, start with a double bond maybe, and then off that carbon you've got a CH3. And a CH3, C, then H, a CH2, OH, there's no carbon there with 4 groups coming off it. This stuff is an ether, CH3, then O, CH2, CH3. It's not that, because all of the carbons have got 2 things that are the same at least. And finally, this is the right answer. That's quite hard to see what's going on perhaps with this structure. But CH3, and then a CH, so C attached to H, and the C is also attached to OH, so it looks like displayed, and then CH2, CH3. So this carbon here has got 4 different groups coming off it, a CH3, an ethyl, an H, and an OH, so that's the right answer. Question 4, what's not a structural isomer? Well, pentan-2-ol clearly is, it's just shifting the OH along 1 carbon. 2-methyl pentan-2-ol has to be the right answer. So pentan-1-ol, 1, 2, 3, 4, 5 carbons and an OH. 2-methyl pentan-2-ol has got 1 more carbon, so it's 4, 5. There's the pent, 1, 2, 3, 4. Oops, I've done too many. For B is 1, 2, 3, 4, 5 carbons, and the pentan-2-ol and 2-methyl pentan-2-ol. Well, pentan-2-ol's got, pentan-1-ol's got 5 carbons. This thing's got 6. This can't be an isomer, so it has to be the answer there, B. And the others are isomers. Mostly that was done quite well, that question. Question 5. Halogenoalkanes can undergo SN1 or SN2. Which will react faster? And I mentioned in the lesson that larger halogens react faster than smaller ones because they're bigger, and that means the bond is weaker between the halogen and the carbon. So it's either the iodo 2-methylpropane or iodobutane. But the other factor to consider is that it's typically faster for tertiary halogenoalkanes to react, so that's the answer there. Isomers of pentane, well, I would just draw them. So I'm going to draw them skeletally. You might want to draw them out fully. 1, 2, 3, 4, 5. So we'll do 2-methyl pentane. Well, that makes no sense. 1, 2, 3, 4, 5, because it's going to have an extra carbon, so that ain't one. Methyl butane, 1, 2, 3, 4. We put the methyl there. It's not given a number because it can't be 1-methylbutane because that's just pentane. And wherever you put it here or here, it's still called 2-methylbutane. So that's the molecule. And dimethylpropane, 1, 2, 3 carbons to the propane, and dimethylpropane. So again, that's got 1, 2, 3, 4, 5 carbons, and it's an alkane. So it has to be this one and this one, 2 and 3, which is C, and that's the right answer. Okay. So question 7, which reactant could form the compound below? So some people found it a good idea in this, and I would agree to, firstly to show how you'd make that. You'd make an ester from a carboxylic acid, that carboxylic acid, and that alcohol. So that if I say that carboxylic acid, I mean an OH where the pen line is, and then an H where that pen line is, like that. And so that carboxylic acid is 1, 2, 3, 4. So it's butanoic acid. Well, there you go. That's the only possible answer. So butanoic acid, and this is ethanol. So that's right. So that's that one. Some people draw it out fully, and that's fine if you need to do that. Which one's an amide? You've got to know what an amide is. So an amide is a C double bond to O and an N next to that. Now often it's for R, that could be anything really. This could be an H, or it could be something else. And the way that you draw that in the condensed form is like is done for B here. So CH3, CO, NH2. That's how you write amides in the condensed form. This is an ester. Convince yourself if you need to. This is simply an amine. Amines are like ammonia, but just the hydrogen has been replaced by the methyl in that case. And this is drawn in a slightly confusing way. It's an amino acid. Normally we write the NH2 first, but let's write it like they have. So CH2. If you have an NH2 coming off it, and then a COOH coming off. This is actually glycine, the amino acid, and that's not an amide either. So next one, we've got butene reacting with hydrogen bromide. So first of all, draw butene correctly. So some people didn't draw butene correctly. Butene's got 4 carbons, and it's but-1-ene, so the double bond has got to be from one of the end carbons. So you must get it right that each carbon is making 4 bonds. That means that this carbon, the internal carbon of the double bond, if you like, the one that's in the middle of the chain, has only got 1 hydrogen on it, and the one at the end has got 2 on it. You've got to get that stuff right, otherwise you're going to lose a mark. And it reacts with hydrogen bromide, and I showed you, remember, that you've got to ideally show the polarity of that polar molecule there, and that's attacked from the center of the double bond, the pi bond, if you like, and it's that pi bond, that negative electron cloud, that attacks the H plus, or sorry, not the H plus, the delta plus hydrogen. That causes this bond to break, and this second arrow was required. You needed both of those for the first mark, I seem to remember. And then you have to draw the intermediate, so draw it fully and carefully. And there are 2 possible intermediates. One with the cation at this position. I'm going to draw the hydrogens that were there before. So either the cation could go at that position or that position, and this hydrogen could go at the other position, right? Of the 2 possible carbocations that could form, this one with the carbon in the middle of the chain is the one that's more likely to form. And I think you're told in this question you've got 2 possible products, but you only get, in this case, only 1 product is formed. It's not just major and minor, it's only 1 possible product. It's only 1 product that actually forms here. When you form that carbocation, you also form Br minus ion, and that Br minus ion attacks that carbocation to give the product. Now some people drew the carbocation in the wrong place, so the carbon at the end, losing a mark. Some people drew the arrows not coming from the correct place, and not coming from the centre of that bond, not from the centre of that bond, not from the lone pair or the minus charge. These are things that lost quite easy marks, I would say. That's meant to be the BR there, isn't it? And I think you got 2 marks for a correct mechanism there. I haven't got the mark scheme just to hand. That's it. Let me just check. I think we've got 2 marks for those. Yep. So you got that lot for 2 marks to get all of that. 1 mark and then 2 marks. And then for the explanation, you have to say that this carbocation is formed preferentially to the alternative carbocation. So preferred carbocation, because it's more stable, or it's the more stable carbocation. So that really for 1 mark, and then explaining that by saying, well, this one's more stable because alkyl groups, and by alkyl groups I mean CH3s or C2H5s or any sort of carbon chain that's surrounding a carbocation makes the carbocation more stable because they push electron density towards it. It's a kind of an inductive effect through bond effect. There's other reasons and other explanations for it. You don't need to know. All you need to know is that some electron density is pushed towards that carbocation, making that carbocation more stable. And so that's what the last mark is for, saying you've got electron releasing alkyl groups, or 2 electron releasing alkyl groups, making that more stable. Okay, let's close the page. And you really should say something about a positive inductive effect there as well. So, but anyway, chloroethene. So first of all, let's draw chloroethene correctly. So I'm going to draw it up here, which a lot of you did as well, to see what it is you're working with. This question is a real tricky one. It catches lots of people out, so I quite like it. I think it's a good one to get you thinking. But that's chloroethene. Now, you've never seen a reaction of a chloroalkene directly. You've never seen that carbon be attacked there as if you would for a halogenoalkane, right? It doesn't happen in the same way. You have seen lots of examples of double bonds being converted into single bonds, though, in lots of different circumstances, I'm sure. And that's the first step here. Now, so the first step is, if I write this out in the condensed form, because we're writing an equation here, so CH2, CHCl, that's that, okay? Now, if you turn that into the chloroalkane, so CH3, CH2Cl, and if I write that up here so you can see what I've done. If you'd written it like this as well, that would have been fine. So I'm just adding hydrogen, HH, across that double bond, gives you that molecule. It's an addition reaction, and that's what you would get there. That thing, if I asked you how to turn that into ethanol, you'd tell me very easily. You'd tell me you react it with hydroxide. And so that's what you need to do for the next step. If you wrote NaOH, that would have been okay. It wasn't asking for a mechanism, it was asking for an equation. And if you'd written NaCl instead of Cl minus, if you wrote Na there, that would have been okay as well. So that one's quite a tricky one, because it would involve 2 steps. But if you know your chemical reactions well, then you're in a decent place. The next question was a bit mean because it did ask you to state the reagents, and you're not, I think, for this particular course expected to know the reagents, but you've done it enough times to know that you can use an oxidizing agent there, and really the oxidizing agent of choice is potassium dichromate in sulfuric acid. So you need the H plus of the acid to help or enable the chromium 7 to turn into chromium 6 to turn into chromium 3. That orange powder that you used, orange solution, if we dissolved it up for you, you need the H plus to be able to get that to convert to chromium 3 plus and to allow the reaction to happen. So that was 1 mark. If you gave another oxidizing agent like potassium manganate 7, I'd have given you the mark for that. Or even if you said an oxidizing agent, I would have let it go at the moment. And you have to know that for primary alcohol to carboxylic acid, this you definitely do need to know, that you need to heat under reflux. and that converts the primary alcohol out to an aldehyde, which then converts to the carboxylic acid. If you mention distilling at all, that's the way that you get the intermediate aldehyde formed. We've done enough of that in class B to know what I'm talking about there. You have to then show 2-chloro-3-methylbutane. Again, draw these out fully, nice and neat displayed. Okay, so start by drawing the butane, 4 carbons, 2-chloro, put a chloro in the second position, 3-methyl, and then whack on the hydrogens everywhere. And then it's a case of applying what you've done a load of times to a molecule perhaps you've not seen before, and then you should be labelling the delta plus and the delta minus and attacking the delta plus with the lone pair of the hydroxide. And because it's SN2, it's the concerted reaction where both parts of the process happen in one step. So this is the one-step process, and you end up getting the transition state formed. Now, these are quite hard to draw, but I was quite pleased with how well you cope with the transition state, those of you who drew one. But I always start by drawing the carbon, and then I've got to have 3 things coming off that carbon. So I'm going to draw, it doesn't really matter where you draw them, so we don't know anything about the stereochemistry of that carbon. So one of them is a hydrogen here, one of them is a CH3, which I've drawn there, and the other one is this side chain. A lot of you simplified that by saying CH, CH3, so that's quite a neat way to do it. So there's the CH and CH3, CH3. You could have drawn it in full as well. And then you've got to have, with the transition state, the bond forming and bond breaking at the same time. Now you have to have the O and the H the right way round. If you've written OH there, that implies that the hydrogen is bonded to the carbon directly. That doesn't happen because hydrogens only make one bond. It also showing the carbon-chlorine bond breaking, and that whole thing has got to be negatively charged because there's a 1 minus on all the reactants, so there must be 1 minus on the transition state, and some people lost a mark because they drew the product correctly, and I would just draw the same thing again in the same way. You're much less likely to make a mistake, but replace the Cl with an OH. But you mustn't forget, as some of you did, to put the Cl minus there as the byproduct you can get. This was reasonably well answered. Hydroxide is a better nucleophile than water. Well, hydroxide is OH minus and water's H2O. And you had to say, some people said it's more negative than water. Well, water's neutral, so it is negative, so the fact that it's negatively charged. And therefore, if it's negatively charged, it's more attracted to positively charged things, so greater attraction to positive centres or the positive carbon or whatever it might be. What does the mark scheme say? Take a quick look. Greater attraction to the carbon atom, or with partial positive charge, something like that. Stereoisomers. I was very picky about this one. You must say same structural formula. Structural formula is same molecular formula but different structure, different arrangement of atoms if you like. But stereoisomer is same structural formula for 1 mark, and then the second mark is different spatial arrangement or different arrangement in space. What that means, what I was referring to, is either cis-trans or it's referring to optical isomers. There's 2 forms of stereoisomers that you've been made aware of. Okay. There are 4 possible structural isomers with this molecular formula, and one of those has got 2 optical isomers. In other words, there's a chiral form of C4H9Br, and that's what it's asking us to focus on, so that's what we're going to focus on. So it's got to be something we can work out quite easily. So just be brave, be bold, and I'm just going to start showing you. So if I draw C4H9, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we put a Br there, something like that. Well, that's not chiral because this carbon here, it's not got an optical isomer, this carbon's got 2 hydrogens on it. So it ain't that, so just get rid of it. What about if I put, 1, 2, 3, 4. What about if I put the bromine here? So 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And this carbon here, if I put them all on now so you can see, but this carbon with the bromine on, the second position, is chiral because it's got 4 different things coming off it. It's got an ethyl, CH2CH3, a methyl, an H, and a Br. So that's the thing that we need to draw. You get 1 mark for drawing that molecule, or do you? I don't think you do actually. I think you have to draw it properly. So then let's draw it properly. So always start by drawing the carbon, the chiral carbon first, and then always the same, always the 4 things coming off it. And we practice this, so can you practice it some more, some of you, so that you know how to draw it? Your tetrahedral carbons should look like that, always. And then all you've got to do is add the bits to it. So it doesn't matter which way around you put them. So I'm going to put CH3 here. I'm going to put an H there, a Br there, then put the ethyl at the top, CH2, CH3. Please be careful when you're drawing these. Make sure the carbon is attached to the correct carbon. People had all sorts of strange things that didn't make sort of chemical sense. And then the best thing really to do is to draw the mirror image of that if you can, or draw it identically the same way but just flip 2 of them. I don't mind which way around you approach it, but the way that I normally do it is by drawing the mirror image. And those molecules are enantiomers of each other. And the way that we could distinguish them in the lab, this means, it's not very well worded, this question, I grant you, so some people didn't know what it was getting at there, but if the way that you can tell you've got 2 optical isomers in the lab is you can pass plane polarized light through them. You must write out plane polarized light, but I'm too lazy to right now. So you must pass plane polarized light through them, and that light would be rotates in opposite directions. One would rotate it clockwise, one would rotate it anti-clockwise. Some people started talking about racemic mixtures, some people started talking about all sorts of things that would just, this is straight from the notes. Nitrobenzene, benzene can be nitrated, so C6H6 can be turned into nitrobenzene, right? I gave you the reagents for this because you're not required in the new spec to know the reagents, and the reagents I told you were conch nitric and conch sulfuric acid, and I gave you a mark for that even though I told you what it was. Okay. One of those, and I also told you how they react, which is the first step of this part down here. So I also told you that they react together in this way. It's an acid-base process that first of all generates H2, I'll show you. First of all, you get H2NO3 plus, because this is acting as an acid, this is acting as a base. Even though it's normally an acid, hydrogen jumps from one there to there, and that thing breaks apart, collapses, we say, to give you the nitrating agent, which is NO2 plus water, and then what's left of the sulfuric acid. Okay, so that's, again, I also told you that and gave you a mark for it for this part of the question. So what's doing the work there? Well, the sulfuric acid is acting as a catalyst in that reaction, and so you don't need to write it in the overall equation. I did also tell you, by the way, you have to heat under reflux, and I gave you the mark for that as well because I was feeling generous. So if H2SO4 is the catalyst, the reactant or the reagent must be HNO3, and if you work it through, 6 carbons, 7 hydrogens, well I've got 5 here, so there must be 2 more, 1 nitrogen, 3 oxygens, well there's 2 here, so there must be 1 more, so excuse me, the overall reaction must be that, and they got the 3rd mark there. This reaction of benzene and something like NO2 plus or E plus, as we called it in the lessons, in the kind of generic example that we did. That reaction, as you should know and should have written, is the it's the name of the mechanism. Lots of people said nitration, but it's the name of the mechanism. So it's electrophilic, and it's substitution that benzene undergoes. And that mechanism it's got to be just right, and was learnt by some of you imprecisely, and not learnt by some of you. So the way that it works is the electrons that make up that pi system, so 2 of those electrons attack the nitrogen of NO2. If you want to be convinced why it's the N that's being attacked, I'd suggest drawing the Lewis structure of NO2. Perhaps see it better. Then we form the intermediate. So we've got the carbon that's got a hydrogen and now an NO2 on it. Some people drew a plus up here, which is wrong. The plus is now in the ring, and we've got to draw a semicircle to it with the opening of the semicircle pointing to the carbon that's got 4 things on it to get the mark there. And then you've got to show the reforming of the aromatic ring. So at the moment this is only 4 electrons, 2 electrons that from the center of that carbon-hydrogen bond end up reforming that circle, removing that positive charge, and you end up with H+. And some of you finished it off nicely by saying, or kind of showing that hydrogen sulfate reacting with the H+ to reform the catalyst, which I didn't give a mark for, an extra mark. You got 5 marks, so you got 1 mark for that, 1 mark for that, 1 mark for that, 1 mark for that, which I gave everybody, and 1 mark for the name. I think that's right. So 5 marks for that, and that's it, folks.